In this section, we're going to look at two more tests for checking series for convergence or divergence, and these are known as the ratio and the root test. Now, if we look at this motivating example, we're looking at the series as the sum runs from 1 to infinity of n 2 to the n over n factorial. And we think back to the kind of tests we know already how to apply. Well, for one, the integral test. Since there's a factorial present in this term for the series, it means that essentially the integral test is out, because there's no underlying function that we can define on all the real numbers which has corresponding values at the integers n times 2 to the n over n factorial. That factorial is causing a problem if we want to extend it to a function for any real numbers. Factorials seem to only make sense when we're looking at integer values. But remember, our ultimate goal is to try to figure out, do the terms of the series go to 0 fast enough to guarantee convergence? And here our terms are given by n times 2 to the n, so an exponential in the numerator and a factorial in the denominator, and we want to decide, does a factorial grow faster than an exponential, and hence causes the term to go to 0, but go to 0 fast enough to guarantee convergence? Well, that's where these two tests come in, ratio and root tests. They are yet further examples of tests which allow us to check, do the terms go to 0 fast enough to guarantee convergence. Now, these ratio and root tests, they can be used to apply to any series, not necessarily when the terms are always positive. The integral test, the comparison test, there we were assuming that all the terms of the series were positive. Now we're extending our tests to be able to apply to series where the terms are not always positive. Last section we looked at the alternating series, and those are where the signs had a predictable behavior to them. It was plus, minus, all the way down the series. But there could be situations where there isn't a predictable behavior to the signs. They could be sporadic, in which case we need tests that can be used to apply to those series. And the way we're going to do this is we're going to replace the series where the signs could bounce around with a series where the terms are all positive. And so that leads us to our first definition. If we consider a series, the sum of an, we call it absolutely convergent if the corresponding series of absolute values is convergent. Okay, so this means we can decide whether a series is absolutely convergent by just ignoring the signs and looking at the series of positive values, and that we have the tests available, such as the integral test and comparison tests. So for example, this series down here, the sum of negative 1 to the n plus 1 over n squared, we would call that an absolutely convergent series because the series converges if we ignore these negative signs that crop up. So if we look at the underlying series of just positive terms, series of absolute values, that is convergent. So we say the original series is absolutely convergent, meaning that the series of absolute values converges. Now there are some series where the only reason the series converges is because of the presence of those negative signs. For example, we've seen this alternating harmonic series, which goes 1 minus a half plus a third minus a quarter plus a fifth and so on. So this alternating harmonic series is convergent. We saw that last lecture. There we used the alternating series test to show that that was convergent. But we know that the only reason it converges is because of those negative signs being present, these alternating signs that come up. And that's because if they weren't there, then the underlying series is the harmonic series, which we know diverges. So we would say then that this series is conditionally convergent. It's conditionally convergent because it's converging only because of the fact that there are negative signs appearing, only because of the condition of how the signs are placed in the series. Now, one of the nice things we have is a connection between absolutely convergent and convergent series. If I want to check a series for convergence, and let's imagine that the series, the signs can be positive, they can be negative, there's no predictable pattern to how the signs are changing, it's not alternating. If I want to check the series for convergence, I can check first to see if it's absolutely convergent, and that is just look at the absolute value of all the terms, ignoring signs. And if it's absolutely convergent, then this theorem says that if it's absolutely convergent, then the series itself must be convergent. So what this means is we can test series that have signs, sporadic signs appearing in them, just by looking at the underlying series of positive terms. And that opens up all our tests to us: integral test, comparison test, etc. Let's have a look at an example. So let's determine if this series is convergent or divergent. Now the issue here is this sign of x, sign of n, can be positive or negative, depending on the n value. And it's not alternating. I mean, it may be positive a couple of times in a row, it could be negative a couple of times in a row. So it's not alternating. And the question is, does this series converge or diverge? So what we'll do is we'll consider the series of absolute values. Now this is just a series of positive terms, so we are free to apply the tests that we've learned so far. And in this case, we can notice that the terms of this series compare to the terms of another series that we know how to deal with. So we notice that the absolute value of sine n over n squared plus 2n plus 1, well, sine of n is smaller than 1. And the denominator, n squared plus 2n plus 1, well, that's bigger than n squared, so the reciprocal is smaller than 1 over n squared, and so we get this inequality. And since the sum of 1 over n squared converges, that was a p-series with p equals 2, and we could get convergence, of course, by using the integral test, then the sum of the absolute values of our original series converges. And this is by the comparison test. Okay, so our series of positive terms converges, but that means then, so that implies that removing the absolute value signs and now letting the terms be positive or negative as they may be, this is absolutely convergent. Just remember, the definition of absolutely convergent said that a series absolutely converges if the corresponding series consisting of the absolute values of the terms converges. And that's what we have above. We have that the series of absolute values converges, so our original series is called absolutely convergent. And then by that previous theorem, since the series is absolutely convergent, we know that it has to converge itself. And that was by the previous theorem. And so there we go. We have that the series converges. And just to summarize how we did this, we checked to see the convergence of our series by looking at the corresponding series of absolute values, found that that converged by the comparison test. So our series here was absolutely convergent and therefore converges.